Hello, I'm Dr. Steven Steiner, and I'm here at DLR in Germany with Dr. and Professor Barbara Milow, who leads the AeroGel research group here at DLR. Barbara, thank you so much for talking with me today.
Yeah, thank you for coming and making this interview with me.
So can you tell me a little bit about yourself? What's your position and what's the nature of the research you do here?
Yeah. We are working on aerogels, and I'm the head of the department of aerogels inside the Institute of Materials Research. And we are located in Cologne in the site of the German Aerospace Center.
So tell me about the German aerospace program. What kinds of things is it involved in, and how do you support that organization?
So German Aerospace Center means not only space research, but also we are looking on aircrafts and energy and traffic.
Okay.
And therefore our department is mainly doing research for traffic applications.
Cool.
And not so much involved to space.
Very cool.
Yeah.
So what kinds of aerogel materials do you make in this group?
We have three parts of aerogels. We have silica aerogels, or hybrid ones in this case also. We have these organic aerogels called more or less RF, and we have biopolymers like polysaccharides.
So can we talk about the silica aerogels you make? What type of silica aerogels are you making, and what are they used for?
So we are doing just silica aerogels, but to give them more properties, we combine them with some reinforcement. So we have fiber reinforcement,
Okay.
and on the other hand, we have also honeycomb reinforcement.
And so what's the advantage of doing something like that?
So you have more strength of the
Okay.
material, and it's easy to handle afterwards.
And so you have some samples here?
Yes, I have one here
Okay.
that is already done with a fire test.
Cool.
And this fire test was done for several minutes. I would say this is more or less 10 minutes.
Okay.
And you can see quite that it is only affected in the range where the fire is coming.
Wow.
And outside it keeps intact.
It's amazing.
So the tile itself keeps intact too. It is only affected on the surface.
That's really cool. And
Yeah.
so what's the application for a material like this?
So these materials are very light,
Okay.
and they are strong, and you can use them wherever you have to protect heat.
So that's actually hotter than something like Pyrogel blanket, which is sold commercially goes. That's only $6.50, so this can go quite a bit hotter.
Yes, this
Very
is
cool.
much better. And the one with the fibers we do,
Yes.
we also add some bromide
Bomite,
particles.
an
to
aluminum
get
material, yeah?
Yes, and this leads to a very strange material which is strong up to 850 degrees.
Wow.
So we see no effect on it.
Very cool.
And this is very nice because you can use it everywhere where you have hot systems. These are our organic aerogels. For sure, they are not as high temperature stable as the silica ones, but they, in many cases you do not need these high temperatures. And then this material is really good because you can process it without supercritical drying.
So this is like the traditional RF aerogel?
Yes,
Like
it's-
originally from Lawrence Livermore chemistry.
Yes, it is a resinol formaldehyde polycondensation, and we do tiles with that, and we do particles, and we do a lot of things with this material.
Can I hold this one?
Yes, for sure.
It's very light, yeah. That's very nice aerogel. Look at it. It's very big. So,
So-
you must have some big autoclaves that you're able to dry materials like this in.
Yes, but if you use a standard recipe, we call it in our labs, then we do not need this.
Oh, so you can ambiently dry.
Yeah, we can ambient dry them, and this is not for thermal insulation because the thermal insulation of this material is around 60 milliwatt per Kelvin a
Okay.
meter. But they have a huge inner surface,
Yes.
and we can pyrolyze them, and we get the carbon out of it.
Cool.
And this material we use for these foundry applications.
Okay.
So we have the cast parts and all cuts inside. We have to use sand cores. And then we use this material inside the sand cores just a little bit, and we can
Like
absorb.
an additive.
Yeah, additive, yes. And we absorb all this gases coming out of the material during casting.
And so there's another sample here that
Yes.
looks somewhat similar.
We have the Picado recipe, and we have a Nomex honeycomb
Oh, this
inside
is a
or
really,
aramid.
really neat material.
Yeah.
And so, yeah, so this one must have aluminum honeycomb.
No, this is aramid.
Oh, this is like Nomex.
Yes.
Okay.
So we can also use aluminum, but then the thermal conductivity is much higher from the honeycomb.
Sure.
And you use it for other applications. You
Okay.
can use then to embed MOFs, for
Yeah,
instance.
metal oxide frameworks.
Yes, and
Or
they
metal,
are
metal organic frameworks.
yes. And they are normally powders, and you can handle them very easy.
Yeah.
So we put them into the AeroGel matrix, and as this is not affected by water,
Okay.
you can use it as an absorption, and then it is running quite well.
Wow. And so could you use this as a structural material too, do you think?
Yes.
Wow.
Yes.
So
And-
a lot of aerogels are solutions looking for problems, but that's what the value of places like DLR is to go and explore some new ideas and then try to find applications where they can
Yeah.
be beneficial.
That's our work.
Yeah.
We are not doing basic research, we are doing applied research.
Applied research. Very
And we are just in between the universities and the industry. I think you have also seen this material before. It is a cellulose-based material.
Yeah, these are very
And,
popular in Europe. They love the biopolymers
yes.
here.
And we have a machine where we can build these boards.
Okay.
And the size of these boards can be a 30 or 20 to 30 lengths,
Okay.
and as long
Centimeters?
as you want.
20
Yeah,
by 30. Wow.
centimeters.
So you can
yes.
make kind of long,
long,
continuous strips
yes,
or long
yes,
boards.
yeah, yeah.
Wow.
And this material is very, very light.
Okay,
Please
let's
take
try this
it.
one. Oh, it is very light.
Yeah.
And it feels
And it
Kind
is,
of
let me
like-
see, 5-8% of cellulose just.
wow.
And
That's
we
pretty durable. More than a normal silica aerogel.
it is not dusty,
Yeah, it's not dusty.
and it is perfect. But it has a thermal conductivity around 30 milliwatt per Kelvin
Okay,
meter.
sure.
We tried to get it down, but we couldn't reduce it yet with our methods.
A lot of polymer aerogels, in my experience, have higher thermal conductivities, and it's hard to get them as low as silica. But 30 is pretty good.
30 is okay,
Yeah.
yeah. And we can do it between 2 or maybe a 0.5%, but then it is really floppy.
Yeah.
But we are starting with 2% of cellulose up to 6% or 8%.
Okay.
And we are doing it not with a salt gel technique, but it is a salt hydrate melt where you can solve the cellulose. So
Oh, okay.
you know, cellulose is not easy to get
Dissolve,
solved.
right? Yeah. Well, I mean, so cellulose is the structural fibrous material that gives the I guess the structural properties to things like trees and,
Yes.
and grass and
Yeah.
corn, right?
Therefore,
So
it has to be
has to be hard to dissolve.
hard, and it
yeah.
should not be solved in water.
So
and-
cellulose natively is very hydrophobic or water resistant. Is this material then also hard to dissolve and water resistant?
It is not water resistant.
It's not water resistant.
It is, but the structure isn't.
The structure's not. The
So
cellulose
it will-
is, but the aerogel's not.
No,
Right.
yes,
Okay.
yeah.
And that's because of its pores and all the hydrogen
Yes,
bonding.
and if you have the water coming in, it shrinks.
Okay, got
So-
it. So then you can, but you said you can change those hydroxyl groups for hydrophobic groups to make it waterproof.
Yeah, we are trying to do that.
Oh, that's cool.
Yeah,
Oh,
yeah,
nice.
yeah.
So, can you use this to reinforce things then, or what do
Yes.
you use this for?
So this is a nanofiber structure
Okay.
where we have covalent bonded fibrils working together, making
Okay.
this network. And I think you will have some nice SEM pictures.
Okay.
And then you put in a polymer like a resin,
Okay.
and then it is looking like this, and you can look through it. It is,
It's transparent.
yes, it is transparent. This
so-
is only a small broken
Yeah,
thing because
sure.
it was tested already.
Wow.
And the tensile strength is much higher than the material itself.
Okay.
It is higher than the cellulose for sure.
Wow.
And it is higher than the polymer.
So it sounds like this is transparent while this is not. I guess because the index of refraction of cellulose is very different from air. So
Yeah.
with all the tiny nanopores, the light moving through it scatters quite a bit. But in here, the index of the refraction of the polymer, I guess, is similar to the index of refraction for the cellulose, so light can pass through it. So when you add the resin to this, does
Yes.
the material shrink? Or does it stay the same size of the aerogel?
More or less the same size.
Oh, that's really nice.
And you can use all the normal technologies you do, and it is without defects because you have this nano structure and you have the capillary forces in the system.
Capillarity-driven wetting.
Yes.
That's right.
Yes.
Oh, that's cool. Yeah, it's a huge problem in making normal composites is eliminating voids and using vacuum technology to help push them out. But here, it's intrinsically void-free because the capillary action of the resin wetting the aerogel drives it into all the pores.
Yeah, exactly.
Oh, that's very, very cool.
Yes.
Oh, good work. Well,
so
here's
it is
this back.
normally not the you have not in mind with the other people who are working with aerogels. I think we have always this application in mind, and
Right.
that are our ideas.
Are they easier to process when they're composited, if they have the honeycomb or fiber in them? Than
Yeah,
when
for
they're...
sure, because the mechanical strength is improved.
Is
So
improved.
it's easier to handle. Yeah,
Okay.
for sure. Yeah.
Yeah, so this is not
So-
the aerogel blue we typically think of.
No,
this is
no.
this is like, you know,
This is-
plastics blue.
We just colored them.
So what's the application of beads and colored beads?
Colored beads is just for fun.
Just for fun. Okay.
Just it looks nice.
Yeah, it does look
So
nice. But what
we
about the other
play,
beads?
yeah, other beads like these white ones here.
Okay.
They also have a functional surface.
Oh, these ones are very
Yeah.
round. They're like little balls.
Yes.
Oh, and this is from the jet cutter.
This is one of the jet cutter.
Oh,
yes.
these are neat.
We can do up to a size of 3 millimeters and down to 1 micron.
Wow. So what do you think that beads are generally useful for as opposed to
So this
particles
is
or...
for filter applications also. So the cellulose is quite good for humidity.
Okay.
And if we make some functionalization, we can think of absorbing CO2.
Okay.
And this is an application we can use in the cabin of an aircraft.
Okay.
And then you can absorb CO2 and you can absorb humidity
Yeah.
and make the climate in the cabin
Improve
more.
the passenger experience.
Yes.
So you have a really nice laboratory here, and actually, I will note that it is very evident that this laboratory is in Germany. It's very clean and industrial and well designed, so it's very beautiful. Could we take a look around your lab? And
Yes,
look
we
at some
can make a
equipment?
tour to her.
Okay, let's
But,
do that. To start the lab tour off, this is your original supercritical dryer.
Yes, this is the first we used in the first years. I have started in 2005, and this is built, I think, in 2003.
Okay.
And it is built at DLR. Construction was made here, and it's just a chamber for high pressure.
Okay.
You put in the aerogels in the solvent, and then you make an exchange of the fluid with CO2 liquid
Okay.
CO2. And then if everything is changed and you have only the liquid CO2 inside the pores, then you can rise the temperature, and then you get supercritical, and then you can just put the CO2 out by involving it.
Depressurizing,
Yeah.
yeah. And so then
So-
there's a bigger autoclave
Yes,
over this way. Let's maybe take a look at it.
and then we started over. We asked for an autoclave with around 5 liters,
Okay.
and we end up with a 12-liter autoclave because the company who built this had only the material for 12 liters.
Okay,
and
got
they
it.
didn't. So
Okay.
this is just a big screwdriver. You see this over there,
Yeah, giant
and
bolts.
you need some force to
Yeah.
get it through.
Some German muscle.
Yeah, and this is working with CO2, also with liquid CO2.
Okay.
But it is a pump that compromises CO2 up to the level of 100 bar, and then you come in with supercritical CO2 in this chamber, and then you go out with extraction,
Okay.
and then you have this part. It's only 60 bar, and then the solvent is collected in one of these bottles.
So this the pump compresses the CO2, and then you're flowing supercritical
Yes.
CO2
Yeah.
through, as opposed to soaking liquid CO2 and then bringing in supercritical.
Yeah.
And all these controls, it looks like temperature controllers. and
Yes.
Some emergency
Pressure
stops.
control and so on.
Very
Yeah,
cool.
yeah. But you have to decide which pressure at which time, so it does not run automatically.
So it's not a manually inputted,
Yes.
automatically
Yeah,
controlled
yeah,
though.
yeah.
Okay. And so and you have a crane here for lifting
Yes,
the
yes,
lid up and
yes.
down. See, mine we have to just hold the lift
Yeah,
over
you
the
connect
lid
it
over.
here, and then you can pump it up. Yeah.
Very cool.
Yes.
Right, and you don't need to start with something like this. Like you said before, you had your smaller vessel, and we have one that's not that unlike the one you just showed us earlier on aerogel.org, and you can build that for about $1,000. So
Yeah.
it's only when you start scaling up do you need to put more money into it.
We first were thinking of building a second one like this, and
Yeah.
you have to have this material, and it has to be approved material to build up a pressure vessel.
Right.
Yeah. But then we didn't have the material because I forgot to make the stamp on it, and then we asked for a new
Wasn't
one.
certified, yeah.
So we came to this after, and we are very lucky with this.
And so it looks like you have an even bigger autoclave over
Yes.
here. So should we
As
take
the
a look?
team is going bigger, and we
Okay.
would like to have bigger tiles.
Wow, this is a very
yeah.
nice looking autoclave you have here, Barbara.
And it's running. It's 100 bar inside.
Oh boy.
And we have a 50 centimeter diameter.
Okay.
50 centimeters.
So
And-
about almost 2 feet, about 1.5 feet in English units.
Yeah. And you can make inside samples around 30 by 30 centimeters.
Okay.
Because we would like to have a good measurement of thermal conductivity.
Right.
Then
wanna
you
be
need
able
this
to-
30 by 30 centimeter
So that's about a foot by a foot for American viewers. That's a very nice sized aerogel monolith. That's
Yeah.
about the biggest you end up ever or really seeing in most cases. And can you talk about all the other stuff? So this one has
So-
pumped CO2 also?
That is the same system, and we can all use the same procedure with the small one and the big one.
Oh, so
we
you don't have
hadn't-
to change your
we
recipe
hadn't had
at
to
all.
change
You just
anything.
copy it over. And
Just copy it.
awesome. Is this one more automatic than
Yes,
that one?
this is more automatic.
So we have one that's maybe a few $1,000s, one that's about $70,000, one that's about $200,000 as you scale up. So yeah, that's one of the big things too when
Yeah.
scaling up monoliths. It becomes tricky is how expensive the equipment gets as it gets bigger and bigger. But it's a beautiful
Yes.
piece of equipment. I bet you're making amazing materials with this.
So come in here.
Okay.
We have here our furnaces,
Wow.
and these are two of them. And this is a bigger one we use for bigger samples.
Okay.
And this is only for very testing. And we have here only
Maybe
boat.
crucible, yeah.
And here we have a bigger boat, and we can put in this boat.
Okay. Put the
And-
samples in there. Put the boat in there. And
yeah. But you have to take care because the temperature is not always the same in the position.
along the length.
But
so
we
right.
measured everything, and we
Yeah.
know at which place, which temperature. And the door is cooled with water,
Okay.
and then you screw it through, and you make here, put this on there.
So why do you have to
To
cool it?
keep-
Because the metal would melt otherwise. It's too hot.
Yes, yes.
So is this not made of metal? This
No,
tube?
no.
What's it made of?
This is silicon carbon.
Silicon carbide.
Yeah,
Okay.
carbon.
So that could go to maybe 1400 degrees C.
Yeah, but we
Okay.
are just working with 1,000
About
degree.
1,000 degrees.
Yeah.
This is a really cool technique because you can take a carbon aerogel that would otherwise have about 750 square meters per gram
Mm-hmm.
of surface area, and then make it like 3,000 square meters per
Yeah,
gram.
we ended up with 3,500 even.
3,500.
Yeah.
Wow, that's incredible. And so over here, there's something that looks like a smaller tube furnace. Is this for making carbon aerogels too?
No, this is a furnace for the hot disk measurements. So if you would like to have hot disk measurement or thermal conductivity measurements, not only in room temperature, but with higher temperatures, you can use this furnace, and it's up to 400 degrees Celsius.
So this machine tells you how good of an insulator an aerogel is and how its insulating properties change as you go up to higher temperatures?
Yes,
Very cool.
but it's not easy with aerogels.
Yeah.
Because they don't see the temperature, and therefore you measure nothing.
Right.
So
actually,
you have always the same value as at room temperature
Right.
because you do not reach the temperature.
So not only are they really good insulators, but they're really difficult to measure how good of an insulator
Yes.
they are because they don't let heat to them. So it's kind of a paradox. A
Yes,
little bit,
yes,
right?
yes.
Well, thank you so much for showing me this equipment. It looks really, really fascinating, and looks like you're doing some amazing work with it.
Yeah, we try to do our best.
All right, so this is your characterization lab.
Yes, this is a lab. We are doing all the characterization that is necessary to get a good feeling for the aerogel.
Okay, so maybe we can tour the different pieces
Yeah.
of equipment you've got. What's this thing?
This is a HFM, the heat flow meter, and
Heat
we
flow
measure the thermal conductivity. and the thermal conductivity is measured inside. A test is running at the moment, so we
Okay.
cannot open.
Okay.
But you can imagine there's a place for a sheet for about 30 to 30 centimeters, and you make a little bit of pressure, and then you have one side is cold and the other side is
Kind of
warm.
like a sandwich press.
Yeah, so you can adjust the pressure.
Okay.
Yeah.
So what's this device do?
So there we're measuring the density, and the density is the tap density or the envelope density.
Of
the
particles?
One of particles.
Okay.
If you have not a good shape where you can measure the size, you have to use this, and it is just a way to see what is the volume
Okay.
of the material.
So basically, if I can't measure the length, width, and height of an object,
Yeah.
if I have like particles where they're all irregular shapes, you just cram it in here and it presses down on it and it can
Yeah.
measure the volume,
Yeah.
so you can
Yes.
calculate the density.
So you have a dry flow, it is called. This is like a sand,
Okay.
and you put it in this chamber
Okay.
and compress it,
Okay.
and you know then the volume of the material.
Okay.
And then you insert just the granular material of the aerogel and get it inside and press it again, and then you know it's a volume that the
The
material
difference between
is.
the two. Very cool. And what do we have in this corner over here?
Over there we have self-made equipment,
Okay.
and it is for gas permeability.
So how easily gas flows through the aerogel?
Yes,
Very cool.
and that's easy to measure.
Very cool. And then over here we've got some more
Yes.
instrumentation.
Here we look on the thermal decomposition of the material with a thermal gravimetric analysis, and we have it connected directly via a gas tube
Okay.
to the FTER measurement,
Okay.
and then you can see at every temperature what is coming out of the material.
Okay.
That is interesting to know which are the connections in the system.
What's this thing over here in the corner?
This Dynasorb is equipment to measure the gas absorption, and we can make a defined composition of gases.
Okay.
So we can let it flow through the sample, and the sample is inside this tube, and you have 4 measurement places for temperature.
Okay.
And then the absorption takes place, and the breakthrough we analyze with a gas analyzer here.
So you can basically tell with the Dynasorb how much of different types of gases that your aerogel would absorb.
Yes. Yeah.
Very cool.
Yeah.
What's this system over here do?
This is a rheometer where we measure the viscosity of the during the sol gel process.
Okay, so you can
So-
watch your liquid get more and more viscous until it gels.
Yes, and in addition, it has an analyzer for the composition via FTER.
Okay, and so what kind of information do you get out of this? Why do you want to make that measurement?
We need the information of the connecting of the bonding in the
Okay.
system, and you see how the sol gel process is forwarded.
Okay, and then I think we have a few more things here. These are more familiar aerogel
Yeah.
analysis equipment systems.
This is for normal BAT and BGH measurements.
So to measure the surface area and the size of the pores.
Yes, and we need.
I believe this is a TriStar by Micromeritics, correct?
Yes, it is working with nitrogen as an absorption, and we can use also CO2. And CO2, we measure the small pores
Okay, so like
below
the
2
ones,
nanometers.
the ones that you put in with CO2, you can also measure using
Yes,
CO2. And
so-
then this is a picnometer, I believe, right?
Yes, this is an AccuPic, and we make here the measurement of skeletal density.
Right.
So only the backbone, the solid
Right.
material. Of
So not the density you get, the envelope density from length, width, and height and the mass, but the density of just a solid part of the aerogel
Yes.
minus all the
Yeah,
pores.
yeah.
Right. Oh,
And
very
we
good.
combine these both together to have the porosity.
And so this is all.
Yeah.
This is just from the specialty silanes. It's a organically modified silica aerogel with no fiber reinforcement. Wow.
And we do a lot of changes with this material, and fibers, we tested a lot of them.
Very cool.
Short fibers, felts, and so on.
All the permutations. Very good. Well, thank you so much for showing me the analysis lab.
Yeah, we are welcome.
Barbara, thanks so much for having me today. I really enjoyed the tour, and it looks like you're doing amazing things with aerogels here at DLR.
Thank you. It was also a pleasure for me to have you here.
Thanks so much. For AeroGel.org, I'm Dr. Steven Steiner, reminding you that aerogel is not just for NASA or DLR anymore. Log on and get involved. Thanks for watching.